Hi, welcome to PyConIL 2021. Today I'm going to be talking about from research to production minus the boilerplate with PyTorch Lightning. Before I get started, let me tell you a little bit about myself. My name is Bornstein. I'm originally from the United States, though I've been living the past 5 years here in Israel. I did my undergraduate degree in Baltimore in history and computer science. For the past 7 years, I've been working with Microsoft in deep learning research, developer advocacy, and open source engineering. At the same time, I've been studying at Bar-Ilan in the Natural Language Processing Lab, where I've done my master's research work on cross-document coreference resolution. More recently, I joined Grid.ai to head up developer advocacy around PyTorch Lightning. Today, we're going to talk about three core topics. We're going to talk about deep learning boilerplate and the challenges that causes when you're developing research code. We're going to talk about PyTorch Lightning and how it helps solve some of those challenges. We'll talk about some recent innovations. And then we'll transition with talking about how we can go from research training of models on our laptop to production scale using Grid. Talking about the challenges of deep learning boilerplate. And to do this, let's first define what boilerplate code is. Boilerplate code is non-standardized code, often very complex code, that's repeatedly rewritten again and again by different developers, even though there's very little functional variation. So in deep learning, this could be all sorts of things that typically go into your standard training loop. This could be accelerators, checkpointing logic, logging, and optimization. The lack of standardization in deep learning boilerplate leads to a lot of challenges when it comes to focusing on research rather than engineering code. First and foremost, because there's no standardization, code is hard to reproduce. Often when we're developing models without the standardization, we might just save model weights, but there's a lot of information related to how we split our data sets, how we choose hyperparameters, how we even formalized random speeds that often doesn't get captured because there's no standardization in boilerplate. In addition to being challenging to reproduce, often deep learning boilerplate makes it hard to reuse code. When different trained logic can be scattered across multiple different scripts or in many different places, it's very hard to take that code and identify exactly what's going on where. Additionally, functionality, like the hardware that a specific function or specific tensor is running on, is often hard-coded. For example, if something's using CUDA, if I have one piece of code that's hard-coded for GPUs and another code that's hard-coded for TPUs, I have to do significant refactoring to merge that code and reuse it. Another challenge is because the code is all over the place, it becomes very hard to debug and understand what's going on where. Lastly, it becomes very difficult to scale because there's that strong coupling between how we're developing code and often the hardware that we're running on top of. It requires significant code refactors to scale to many devices or different types of devices. So when we're thinking about all these challenges caused by boilerplate, what if we didn't have to deal with them? What if instead of being hard to reproduce, our code was self-contained? What if instead of being hard to reuse, all our code was modular and standardized? What if instead of being hard to debug, our code was organized so we could identify exactly what's going on? What if we had granular logging at each of the different layers of our training, validation, and testing loops? And what if we had built-in visualization? And what if instead of being hard to scale, there was no dependency between our research code and our hardware? This is what PyTorch Lightning enables. PyTorch Lightning addresses the challenges of boilerplate through four core design principles. First and foremost, all our model and data code is self-contained, which enables reproducibility, as well as enabling us to mix and match models. Next, we modularize our code through a consistent standard. If we look at the traditional machine learning development environment, we traditionally mix our research, data, and engineering code. With Lightning, we take this code, we separate out all our research code into the abstract class of the Lightning module. We decouple our data code into the data module, and the remaining code later can be abstracted out and managed by Lightning, which leads us into our next design principle. Lightning reduces the boilerplate by offloading these standard patterns. So if we look again, we have our Lightning module and we have our data module. We let Lightning handle the engineering boilerplate code. This is where most of our errors come. This is where if we forget our .eval or our .backwards, or if we have challenges with our CUDA, all of this is managed for us by the Lightning trainer. And the last core concept of Lightning is it's all well and good to reduce boilerplate, but it needs to be functional, and users need to have full flexibility. So if you can develop something in PyTorch, you should be able to override what you need and be able to do the same functionality in a cleaner way with Lightning. These design principles enable all sorts of really amazing features right out of the box. For example, if we have code that runs on a CPU, just by adding the trader flag GPU equals 1 without making any changes to our research code, automatically we leverage a GPU. And we can scale this. If we change that to 8, now things distribute across 8 GPUs. We can even scale this further across multi-node clusters. This is done through the accelerators callbacks, and Lightning supports multiple accelerators out of the box, such as Horovod, DeepSpeed, DDP, without requiring you to make any changes to your code, making it very easy to experiment with multi-node and distributed training. Additionally, we provide features and callbacks such as automated version checkpoints, custom support for loggers and logging through all the common libraries, weights and biases, TensorBoard, Comet, MLflow, Neptune Logger, and many more. We have direct integration both with the Lightning profiler, which allows you to very quickly see and debug your code. We also have native support with just one flag for the PyTorch profiler as well. Everything is rigorously tested through CI/CD, so you know that when you're using Lightning, your code will run across different operating systems and Python configurations, whether you're running on a CPU, multiple GPUs, or even TPUs. There are many, many, many more features. We'll get into a couple of them later when we talk about latest developments, but this also enables things like on-X export quantization, stochastic weight averaging, pruning, and many, many, many more features. The Lightning API works through a couple key concepts. The first concept is the Lightning module, as we discussed. This is responsible for decoupling your model code from your research, from the engineering code. It improves readability as each phase of your code is organized within the simple abstract library. It's very easy to convert your existing PyTorch code to fit this framework. The next concept is the data module. This is where we decouple data logic, managing things like transforms, splits, seeds, downloading data. This also improves readability and improves reproducibility through the standardized API. Once you've done this, the core entry point is the trainer. As we saw before, the trainer enables you to take advantage of all the callbacks. This is what enables you to reduce the majority of your boilerplate. Additionally, all the callbacks through the trainer are fully customizable and overridable, and you can even extend them with your own. The functionality is fully encapsulated. So here's an example of a print table metrics callback. There are many out-of-the-box callbacks that you can play around with for inspiration that enable things like early stopping and monitoring and the like. Additionally, there's Torch metrics, which contains 25 plus optimized, easy to read, easy to extend metrics implementations that can fully leverage whatever hardware you're running on. They're rigorously tested, and they also work with standard PyTorch. You can even add your own metrics, and it makes it very easy to write clean and reproducible code, and we're constantly looking for community support to contribute more. The last concept is the accelerator. This is what decouples your hardware from your machine learning code. We have a better understanding of how PyTorch Lightning reduces the boilerplate and some of the core features it provides. I'd like to take this time to discuss some of the latest innovations that we've provided to the Lightning framework. To start with, we've introduced many new callbacks, including a callback to enable easier fine-tuning of your models. This base fine-tuning callback can be extended and enables you to implement different fine-tuning strategies, like the ability to freeze your model before training and unfreeze between different epochs, or have granular control over which layers to freeze at each stage of fine-tuning. Additionally, we have callbacks for model pruning to enable you to have smaller models with the ability to implement the lottery ticket hypothesis. We've implemented quantization-aware training that enables you to even further make your models smaller. Stochastic weight averaging with just one line that enables you to generalize your models. DeepSpeed integration. So instead of you having to reconfigure a lot of your code, here you can take advantage of the latest developments of DeepSpeed. We partnered with Microsoft to demonstrate how you can scale models up to trillions of parameters. We worked to take work done by Andrew Karpathy on MinGPT and scale it to over 45 billion parameters on a Lambda A100 with just 8 GPUs. You can see that this is configurable without having to refactor any of your code. All the boilerplate is abstracted for you. Additionally, recently PyTorch announced a new profiler to enable better debugging and awareness of what's going on at each phase of PyTorch execution. Instead of you having to modify your code, this is accessible with just one flag, profiler equals PyTorch. One of the feedbacks that we've gotten from the community is requests for a CLI to enable more configuration of Lightning jobs to enable more automation. So we've developed a new Lightning CLI with a simple API. It enables you to generate rich help around your model compositions. So you can see that if I want to run multiple runs, I can configure everything through YAML, in addition to the traditional arg parse or using other packages. Additionally, we have some new developments around Lightning Flash. Lightning Flash is a task hub that makes it easy for you to do fast baselining, inference, fine-tuning, and iteration of common deep learning tasks, such as image, text, and tabular classification, object detection, image embedding, summarization, translation, and more. We're constantly adding new tasks all the time, and we'd love to get the community involved. As part of this, we've introduced new backend APIs for Lightning Flash that enable you to have more granular control over how data is pre-processed and post-processed. Additionally, we have a full reference implementation through the base visualization callback, which I'll get into in a second. And we've developed a backbone API that allows you to extend tasks with any model hub you'd like, as well as add your own and contribute your own backbones to Flash. So to look at an example of the end-to-end data processing pipeline, we've developed a visualization callback. This visualization callback enables you to visualize any batch at any stage of your transforms. For example, if I have cornea transforms today, maybe I would want to visualize a batch, but I'd also like to visualize how my different transforms impact my model for doing pre-processing and post-processing, or to debug that way. And now I can with the visualization callback. At every stage, I can do visualization, and I can even customize this myself. Additionally, through the Backbone API, we have 400 plus backbones enabled. Through Hugging Face and Tim, you can extend this with any model hub. It's very easy to use. We've also developed a new framework. One of the common requests that we've gotten from the community is how can we take advantage of PyTorch Lightning to train Hugging Face transformer models. To address this, we've created a research library called Lightning Transformers. Definitely recommend you check it out. For more information, please check PyTorch Lightning in the docs. We have a huge community of 400 plus contributors. We recently crossed the threshold of 2 million downloads, and we have tens of thousands of active users. Now that we've discussed how PyTorch Lightning helps address the challenges of deep learning boilerplate and some of the innovations that help you take your deep learning code to the next level, I want to discuss how we can do production scale training on the cloud through Grid. Training at production scale is hard. Today, if we're managing this ourselves, we have to manage package dependencies, ingesting, versioning large data sets, managing and scaling distributed compute and cloud infrastructure, coming up with visualization logic for logs, managing model assets, and doing this in a way where its cost is not very clear. There are a lot of ML ops options out there, but there's a lot of complex configurations that they require. And we believe that training at production scale should be as easy as training on your laptop. If you can run your deep learning project on your laptop environment or on GitHub, it should just run in the cloud. That's the fundamental principle of Grid.ai. Now that we've reduced the boilerplate with Lightning, we can take advantage of those features and train at scale without all the overhead of traditional ML ops. I'm going to show you a quick demo of how this works. We'll go here to, this is the Grid.ai platform. To get here, we just go Grid.ai, and you can log in for free and get started with just a GitHub or a Google account. Once we're in the platform, we can upload or manage our data either through the CLI or by creating new data stores with a simple click and drag interface. We can even select and upload data from remotely hosted files. From there, we can iterate and experiment through sessions. Sessions can be connected through Visual Studio Code, directly SSH'd into. They get started up within just a few minutes. And you can access everything through Jupyter Lab as well, just through the simple UI. From there, we can also scale, and once we've created a baseline for ourselves, scale and experiment with runs. Runs are really cool because if you have code hosted in GitHub, it's as simple as copying your script and Grid will do the rest for you. So here we have in our documentation a bunch of examples. For example, the MinGPT example of how you scale with deep speed can be reproduced in Grid. We also have examples showing how to use Keras and TensorFlow as well as how you can leverage some of the innovations we talked about with Flash. Here, I'll show you how we can create a quick run with Flash in just a matter of minutes. I can go in here, I create new run, I copy in whatever my entry script is, and then I could link this to whatever data store I want. Then from here, all I have to do is select the compute that I want to run on. We'll take this simple T4 instance to get started. Then I just add in my script parameters. So I tell it I want to take advantage of the GPU. The next thing I'll tell it is I want to run for a max epochs of 5. And we can leverage all the Lightning innovations to minimize the overhead of training. On top of that, we can even do really cool things like parameter searches without having to modify any of our existing training code. So if I want to, for example, configure the learning rate, we can do a quick sweep. You can see here how simple this becomes. So here, this will run 2 experiments. And if we want to add one more experiment, we could do this. And now this will launch 3 versions of my experiment in parallel. And I can implement myself early termination through my Lightning flags without having to deal with any of the boilerplate overhead. Once a run is running, I can view and visualize all the results in real time. So we have all the Lightning metrics that we talked about earlier. We have direct integration through TensorBoard, so everything here can be viewed on TensorBoard as well. You also have access in real time as they're being generated to all your model assets. So you can easily export here, and then everything that you've done can be exported to Onyx or TorchScript and run on the edge. Using Flash, for example, we can do this with just 3 lines of code. So you can see here how flexible this framework is and how quickly it makes it for you. If you have code that will run on your laptop, you just put it in Git, and you can now scale it on the cloud without all the overhead of a traditional MLOps pipeline. A couple quick things to talk about to wrap up here. Grid is responsive, so you have mobile support and you can manage everything on the go. And we have many different tiers, things that are being developed all the time. So definitely keep an eye out. And I definitely recommend, once you've minimized your boilerplate with Lightning, to think about how you can scale your training without all the overhead of MLOps on the cloud with Grid. Thank you again for the time. I'll provide resources here on Twitter and LinkedIn. If you have any questions, let us know in the comments or reach out to me at PyTorch on Twitter and get engaged. We have a vibrant GitHub discussions, Slack, and Twitter community. We'd love to have you as part of it. And if you're interested in contributing or getting involved, I'm here in the Israeli ecosystem. Feel free to come find me. Thank you.